Ah, yes. The sheer memetics of how anime actually help unify physics. Hey guys, what's going on? Memes here. Again, this is a conjecture from a dude on the internet. Take it for what you will. Naruto, refresh us.
I am not gonna die!
He's very determined, young man.
Okay, let's see you dodge me this time!
The first time he uses respect. Oh, look, there's a very heavy
He's channeling
articulation
chakra again, like
of
before.
energy.
Now I see.
He's drawing it
He
in.
made the
He's
clone
finding
to
ways
gather up his
to
chakra.
account for what's
Ingenious.
going on, some may say.
No,
What ends up happening
this is different.
in that whirl of energy there? It starts gathering. Oh, look, it takes
Press
form.
the chakra!
Looks like a 3-sphere.
Keep it
All
going!
right. We as much as I love this is not the point. I can watch that later. I totally recommend it for any of my weeb friends out there. But what does this have to do with anything else that's going on? All right. The conjecture is you take a look at the Einstein equation. It's like, all right, E equals mc squared. There's actually two other components in there because how basically if you have enough energy that has a gravitational effect. It just we're used to observing in the form of matter and everything, but people like, well, you could just have you could technically have what we would call a quote unquote black hole of just energy if it was dense enough. Okay. Now, what if it wasn't necessarily that dense, but if we know there's energy already in the vacuum that's fluctuating, my question is it homogeneous throughout different places? Or if there are areas, maybe say, maybe galactic sized things, star sized things, there might be some energy resonance, some information, if you would, or even just any type of light or any type of frequency leaving it. I mean, part of this came from an Anton Petrov video where they're talking about tidal effects. It's like, all right, so when a star's there, it's basically tearing it apart. I'm like, so if the gravity is so strong there, that's quote unquote warping space time, it isn't that going to be an increase in energy in order to do that? What form that energy takes, what eigenstates and different stuff and things, freaking what was it, symmetries, tensors, what forms that takes, it may depend, but we go over to our good friend Professor Henry Segerman. The link is in the doobly-doo. So basically why I was showing that is if you take a look at this.
Hi, my name is Henry Segerman. This is symmetric figure 8 knot. The figure 8 knot is the third simplest knot after the unknot and the trefoil. This is joint work with Saul Schleimer and François Guéritaud. So this is yet another sculpture which is designed in the three-dimensional sphere, the unit sphere in four-dimensional space, and then projected into R3 via stereographic projection. And that explains why there's these sort of big bulges. The tube around the knot with this grid pattern on the tube is constant thickness in S3, but because these arcs out here are nearer to the projection points.
Basically, since you're dealing with quote unquote hyperbolic space, basically the parabola zone and stuff, when you start looking at this, the claim is this is essentially the fundamental wave action for our realm of persistence, because that gives rise to our next friend over here, as we go back to Professor Henry Segerman's channel as well to check out the figure 8 knot complement. So basically, when you subtract that articulation in there, because it ends up, there's even another video where it shows it's all over the place. It gives rise to this. This is a double cover of the Geesking manifold.
Hi, my name is Henry Segerman. This is figure 8 knot complement.
Non-compact manifold.
And this is joint work with Saul Schleimer and François Guéritaud. So often in knot theory, it's a good idea to look not only at the knot, but also the complement of the knot. So the complement of the knot is what you get when you subtract the knot from three-dimensional space. And you're left with a three-dimensional manifold that has a torus boundary. So you can think of this as I got this sort of ball, and then I've drilled out the knot inside of this, where you can think of a worm eating its way through.
Okay, so this is a bit of a review for other things. We go into that in Eternal Cyclic Cosmology. If you want to check any of that stuff out, you could totally search from the channel if that interests you. But essentially, it gives rise to a spherical-like object that, let's just say, could probably be deformed, because he even mentions in some of these other videos, it's like, you can project this however you want. But what I'm conjecturing is essentially the energy within the vacuum or a vacuum-like state. How much energy do we need to get our measurements for dark matter to account for that? That's why I did the little trolley video before. I'm calling this Uzumaki effect because if something like this does have to do with it, and again, we have Professor Segerman and his collaborators, Saul Schleimer and François, Guéritaud? I apologize, sir. But you look at some of this work, it's covering different flow maps and everything. And especially when you're dealing with the hyperbolic figure eight knot. Welcome, Dr. Smith. Good to see you, my friend. But especially if you start going into, now I'm going to show the window. Boom. All right, so that's a figure eight knot according to Wikipedia, our friend. Links in the doobly-doo. But essentially, this was the object that ended up discovering that William Thurston and a bunch of other folks over the preceding years. I think Thurston discovered this in 1974. So it's within like the past 50 years, even less than that. But he found this gave rise to a hyperbolic complement, and it was a small knot that projected that. And it's the complement who has the smallest possible volume. And that's very interesting because the figure eight knot is considered to be the simplest hyperbolic knot. It's double coupled the Keysking manifold. When we go to the Keysking manifold, one of the fascinating things is the Keysking manifold is a fiber bundle of a circle with fiber. The once punctured terse and monodromy gives oh no, it was up here. It has a double cover. The underlying compact manifold has a Klein model boundary, and the first homology group in mathematics is the general way of associating a sequence of algebraic objects such as abelian groups or modules with other mathematical objects such as topological spaces. Homology groups were originally defined in algebraic topology. That sounds useful for this stuff. Yeah, and the first homology group of the Keysking manifold is the integers. The integers, I believe that's all like the standard like full numbers. If it's all of them, and that gives a double cover, that doesn't mean like, I don't know. That sounds like it might be Turing complete, because if you have a heavy level of articulation that could give rise to complexity, but essentially the other thing is you start looking at this, all right, start to see different articulations. Seems to be moving in different ways. Oh, look, the southwest, seems to have a lot of freedom, and that's mapping. That's from Stack Exchange. But basically, we get to this. This is where I'm bringing up the Uzumaki conjecture, just because it sounds amazing, or the Uzumaki effect. If Professor William Unruh has an effect, I feel Naruto Uzumaki should have an effect. Because if it helps bring you to the idea, why the heck not? But okay. So essentially, we go to, where is this? Okay. So, all right. The dark matter filaments bridge the space between galaxies in this false color map. Locations of bright galaxies are shown by the white regions. The presence of dark matter filament bridging the galaxies is shown in red. All right, so you got your galaxies there. Oh, it's a map of dark matter. Now, I'm just saying if there happens to be a certain level of energy density there, and we don't necessarily have the greatest measurements yet, if we start to explore this, and maybe if we use, I don't know, maybe François Guéritaud, apologies, I'm sure I butchered that, varying triangulations and Cannon-Thurston maps. Because when you start going in here, all right, you're breaking it up, you're analyzing, oh, look, there's a whole bunch of motion going, oh, look at that. That is getting pretty fancy there. I have not read this. Totally got to be fair. You're going through this. I see a lot just from the analysis of pictures. I'm like, okay, you're finding a whole bunch of different ways to measure what's going on. That sounds pretty cool. I know Jonathan Gorad's been working on ways to use basically, tesseracts, basically four-dimensional tetrahedrons to start measure things in the Wolfram Physics Project. I think that's pretty cool. Now again, I'm just conjecturing that perhaps this could lead us to different stuff and things that maybe are worth looking for. And then we go over to, probably one of my favorite title papers ever, From Veering Triangulations to Link Spaces and Back Again. I see what you did there, gentlemen. Thank you so much for the Tolkien reference. I did actually start to go through this paper. It is very dense. I have not finished, but basically they start decomposing the hyperbolic figure 8 knots complement. And you're seeing these different maps, and then I think they do go into some of the flow. Okay, that's a hyperbolic thing. Professor Henry Segerman does have some other videos, but they start going through just how it breaks apart, the different motions, and these are fascinating maps to me. I'm like, I'm not saying we could find a path interval or some interval there or something, but I just think it's pretty cool. So that's essentially my little conjecture here is that basically dark matter, as we kind of understand it, it's basically helping the galaxies. There seems to be additional rotation here, and we can't account for the mass. Well, if we're looking for matter, what if it's just not matter? Well, it's like Professor Keating says, it's like you get an intoxicated gentleman underneath a street lamp, and the police officer comes by. It's like, what are you doing, sir? I lost my keys. I don't see any keys. Where'd you lose them? In the park. I'm looking here though. I'm just saying that I feel like, have we considered that maybe it's energy? Can we measure the energy density of the quote unquote vacuum or a similar vacuum like state or equivalent to see if there's greater energy density in some places? How would we go about that? Only we had some smart experimentalists around. Fist bump. But that's all I got for right now. Please out, everybody. Be safe. And no matter what happens, take care of yourselves. It's a crazy world out there, but I think some great things are going to happen real soon. Take care.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude.